so this is the video to talk about whether we have holes or not for rational functions. Step one, the very first thing you want to do is you want to figure out whether it's a simple rational function or it's complex. Okay, so a simple rational function is going to look something of the format like this, like kind of like the transformation piece, y equals a over x minus h plus k. This one you can easily tell what the asymptotes are. Your asymptotes will be your h and k values. So that's why it's called simple. Your complex ones are going to look more like a variable in the numerator. That's going to be more complex, and we're going to talk about that first. Okay, so if it's simple, it's straight to the point, you have your asymptotes. If it's complex, you need to go to step two. In step two, you want to look for your horizontal asymptotes first. Okay, so you want to follow these rules, and these rules in step two are right here. And I'm sorry, I probably should have moved those up, but we're looking for the degree of p and a degree of q. Okay, so for other words, if the degree of p, because we have the function, I apologize, if it's complex, is p of q, no, sorry, p of x, sorry, yes, p of x, my apologies, p of x over q of x. So basically, these represent two functions, two binomials or monomials or trinomials. And when we're talking about the degree, we're talking about the exponent, the highest exponent to the variable. So for instance, for horizontal asymptotes, if the degree of p is greater than the degree of q, so this is going to look something like this: x squared plus such and such, let's say x squared plus 1 over x, right? The degree of 2 for this x is higher than the degree of 1 for this x. So in this case, because of this situation, we have no horizontal asymptote. Okay, that tells us something about our domain. By the way, if we don't have a horizontal asymptote, we don't have something stopping us from going left to right. Now, on the other hand, if the degree of p is less than the degree of q, so basically this is backwards, right? So let's say this is x over x squared plus 1, right? But you see how I flipped them backwards? So now this degree is 1, this degree is 2. Since p is less than the degree of q, we have the horizontal asymptote at y equals 0. Okay? So when the degree is lower on the top than the bottom, it's y equals 0. And then if the degrees are the same, right? That's what it means, the equals. So let's say x squared plus 1 over x squared, right? See how they're the same. I apologize, probably should have did this in another color. So x squared plus 1 over x squared. Notice the degree is 2 and 2. What you want to do is that your horizontal asymptote y is equal to your leading coefficient over your leading coefficient. And in this case, my leading coefficient's this invisible 1 over 1. So in this situation, it's y equals 1. Okay, so remember that for your horizontal asymptotes. Those are very important. You want to do those asymptotes before you start to reduce. Okay, so step 3, and this is for your complex equations, right? The ones where you have a p of x on top and a q of x on the bottom. Okay, you want to always simplify if you can. Find your GCF and factor if you can. Right, so as an example, let's take this equation, x squared plus 6x minus 2 over x cubed plus x squared minus 6x minus 3. Okay, so before I do anything of that, I go down here, check the horizontal asymptote first. Okay, before I do anything else, right? Always do that. Simplify GCF factor. Here, there's no GCF, but I can factor factors of -2 to add up 6. I don't even think there are any factors there. So we'll keep going here. All right, your x-intercepts is you want to set the numerator equal to 0 and solve. That's very simple. So whatever's on the top, your numerator, set it equal to 0 and solve. Okay. For your vertical asymptotes, these are the ones that go straight up and down, right? In this case, you want to set the denominator equal to 0. So the bottom piece equal to 0 and then solve. Solve for x, solve for your variable, right? Okay, once you do that, you'll get your two pieces. Remember, vertical asymptotes are x equals, your x-intercepts are going to be x comma 0, their actual point for your x value. Okay, so now we're going to talk about holes, because this is probably the biggest issue that many people have. Okay, holes, we don't really call them holes, we call them removable discontinuity. Removable discontinuity. I want to make sure I spell this right. Continuities. Okay, this is when you factor and something cancels out, right? Till you do the x method and something factors, it cancels out. So what does this mean? This means that you have like a little break in the graph, kind of like a hole. That's why they call it a hole. Oops, break in the graph. Okay, looks something like this, like your function, and then there's a little hole, and it goes like that, right? So rational function, notice there's a hole there. Okay, so if P and Q, right, P of x and Q of x, P of x and Q of x have a common factor. So that means like if something cancels out, right? Like let's say x plus 2, you'll see here in a second. Okay, don't forget, once you find that x value, you can plug it in and you can find the actual hole, because a hole is going to have an x and a y value. Okay, so let's do some of these examples right here. That way you can start to see what I'm talking about as far as the holes. We have x minus 2 over x squared minus 6x plus 8. Okay, so before we do anything, before we simplify, obviously this is complex. Notice there's a variable on top, so this is why this is complex. So before we do this, let's check on our horizontal asymptote first. Okay, horizontal asymptote, the degree up top is 1, because the x exponent for that is 1. Here's 2, so that means P of x is actually greater than Q of x. Or sorry, less than. P of x is less than Q of x, which means my horizontal asymptote is y equals 0, okay, which is basically the x-axis, right? So since there's a horizontal asymptote, that's stopping me from going to the bottom or top, so my range changes. So basically it's all real numbers except for y cannot be equal to 0. Okay, very easy stuff. Okay, now before we do anything else, let's go ahead and let's start to factor stuff out. Okay, we can factor out the top, factors of 8, or sorry, the bottom, the factors of 8 that add up to -6. I believe -4, -2. Right, so on the top, I'm going to have x minus 2 divided by, now I'm doing my x method, that's how I'm coming with this, right? So x minus 2 divided by x minus 4 times x minus 2. Right? X squared minus 4x minus 2x plus 8, right? That's how I get that. So in this situation, you'll notice something's going to happen, okay? And in this situation, we're looking for cancel out, simplifying, right? So you have x minus 2, x minus 2. So this means I have a hole, right? And when I discontinue this, right, these two cancel each other out, I'm actually left with this 1 over x minus 4. Now, in order to find this hole feature, I'm going to set this x minus 2 equal to 0. And I'm going to solve. In that situation, that means that gives me an x value at 2. So now I have 2. And now I need to find my y value. So in order to find my y value, I plug this 2 into what I have left over. Okay? So 1 over 2 minus 4. Well, 2 minus 4 is negative 2. So this tells me what I have left over is 1 over negative 2, right? Okay, and that's where my hole is going to be, 2 comma negative 1/2. Okay, all right. So now we set our numerator equal to 0. Well, guess what? 1 equals 0. That's not true. So there's no x-intercept, right? Because we would set our numerator because we simplified. Okay, my vertical asymptote, we set the denominator equal to 0. X minus 4 equals 0. Add 4 to both sides, x equals 4. So my vertical asymptote is x equals 4. So in that situation, my domain is all real numbers such that x is not equal to 4. Okay, and technically, since there's a hole, we have an x value and a y value that we need to put in domain range, but I'm not going to go on from that. Hopefully you guys understand. Okay, and example number 2, the degrees are the same for p of x and q of x. The degree is 1 here, the degree is 1 here. So if that's the case, what this means is I'm taking my leading coefficients. My leading coefficient here is 5. My leading coefficient here is 1. 5 divided by 1 is 5. So that tells me my horizontal asymptote is y equals 5. Okay. Now, after doing that, I check to see if I have anything that can cancel out. I can factor out using GCF or X method, and there's nothing I can do in this example number 2 to do that. So from there on, I can start doing my x-intercepts and my vertical asymptotes. There are no holes because nothing cancels out. Okay, so first, x-intercept, I set my numerator equal to 0. So 5x plus 2 equals 0. Solve for x in this situation, subtract 2, divide by 5. My x-intercept is negative 2 over 5, comma 0. Remember, x-intercepts, y value is always equal to 0. Okay, now that I've done that, I can find my vertical asymptote by setting my denominator equal to 0. X plus 3 equals 0. Okay, subtract 3 to both sides, and my vertical asymptote is x equals negative 3. Now that we have our horizontal asymptotes and vertical asymptotes, I can use these asymptotes for my domain. Since x is equal to negative 3, that means my domain is all real numbers such that x is not equal to negative 3, because that's where my asymptote is. It gets really close to it, but it doesn't actually touch it, right? So same thing here with y equals 5, all real numbers such that y is not equal to 5, okay? One last problem, hopefully this makes more sense, okay? Talking about p of x over q of x, right? These are just two polynomials, right, that we're trying to factor out. Okay, you'll notice before I do any simplifying, I always want to look for the horizontal asymptotes first, because that we're talking about the degrees, the exponents to my variables. Right, here is the power of 2 over the power of 1, right? These are my exponents, those are the higher degrees. So that tells me that p is actually greater than q, right? So what that means is there's no horizontal asymptotes. There's none whatsoever, okay? So there's nothing to stop it, which you're going to see is going to help our range here in a second. And you're going to see why. Okay? So in this situation, x squared minus 3x minus 10, we can factor out the top. So now we got to start simplifying. Okay, x squared minus 3x minus 10. We have factors of negative 10 that add up to negative 3. I have x minus 5 times x plus 2. Okay? Over x minus 3. Okay, all right, so negative 5 times 2 is negative 10. Negative 5x plus 2x is negative 3x. So we're good to go. Notice there's no holes here. Nothing cancels out, so that's going to be good for us. Okay, nothing cancels out. And you're going to notice here there's going to be 2 x-intercepts because I have 2 equations or 2 factors on the top that I need to do. So I have my whole numerator I'm setting equal to 0, right? So x minus 5 equals 0, 0, and x plus 2 equals 0, because I'm trying to find my x-intercepts. Okay, so in this situation, I have an x-intercept at 5, comma 0. X minus 5 equals 0, plus 5, 5, comma 0. Here, my other x-intercepts, negative 2, comma 0. X plus 2 equals 0, subtract 2. Okay, those are my 2 x-intercepts. Okay, Now I look at my vertical asymptote, set my denominator equal to 0, x minus 3 equals 0. Therefore, this tells me that my vertical asymptote is x equals 3. Okay? So with that being the case, since my vertical asymptote is x equals 3, that stops at that line, can't reach that value of 3, so we say all real numbers such that x is not equal to 3. And because there's no horizontal asymptote stopping this function going all the way to the top and all the way to the bottom, it's just all real numbers. Isn't that pretty easy? Awesome. So there's some notes. Hopefully that helps out. Let me know if you have any questions.